Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about different kinds of integrals in Rn. And indeed, in today's part 11, we will look at something we can call integration by parts in n dimensions. And moreover, this will directly lead to some nice formulas that are known as Green's identities. More precisely, these are two formulas for the Laplacian, and they are named after the British mathematician George Green. However, as always, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the Steady membership you can download a lot of additional material, and you can find the link in the description. And now without further ado, I would say let's immediately state the product rule of differentiation in n dimensions. And for that, let's say here we have Rn and maps that are defined on it. For example, we could have something that we call a vector field V, which means it sends Rn to Rn again. And on the other hand, we could also have a scalar field, which means just an ordinary real-valued function defined on Rn. And let's call this f, which means the codomain is just the real number line. And now obviously, since we want to look at differentiation and integration, we should look at continuously differentiable functions here. So in short, we would say both things are C1 functions. But here please don't forget, V has n components, while f has just one component. However, this also means that we can easily form the product of both maps. And then this resulting product is still a nice C1 map from Rn into Rn. So without any problems, we can calculate derivatives here, and what we get is the product rule in n dimensions. So the simplest thing we could do here is to look at a partial derivative of the function f times v. So maybe we just look at the jth coordinate here, so we call it xj. And on the other hand, we can also fix the coordinate vi, which means we only have a scalar function here. In other words, we can just use the ordinary product rule like we have it in one dimension. This means first we have the partial derivative of f times vi plus f times the partial derivative of vi. So nothing new here, we can just use the fact that the partial derivative is essentially a one-dimensional derivative. However, now we can use that to look at the divergence of the product. So this is now the divergence of the vector field f times v. And there you already know, this one is just defined by summing up partial derivatives. The only thing you should keep in mind there is that we have the same index in the component and in the coordinate involved. So there's just j that goes from 1 to n. So at this point we can simply use our formula from above. So this means we sum up two different terms here, one with the derivatives of f and the other one with the derivatives of v. In fact, in the second part here, we immediately recognize the divergence of v times the function f. This is quite nice because it just means that we push the divergence to the vector field v. Moreover, on the other hand, you should see that in the first part here, we have an inner product, the standard inner product in Rn. And actually there, the vector with the partial derivatives of f can be called the gradient of f. So we have the gradient here in the standard inner product with v. And there we have it. This is how the product rule looks with the divergence and the gradient involved. And here please note that in this video I will denote the standard inner product in Rn just by a big dot. This is a really short notation and therefore quite useful, but we should not overdo it. So in the case that there could be some confusion, I will use the pointed brackets again. However, here it's quite useful because it gives us the possibility of an alternative formulation for this product rule. So what I mean is that we can use the so-called Nabla operator to denote the divergence and the gradient. The divergence is denoted by the Nabla operator and the inner product symbol. This makes sense because by definition we have something like an inner product with the operator and the components of the function. Hence, this is the really short notation for the divergence by using the Nabla operator. And on the other hand, the gradient is just denoted as nabla of f. So by putting these two symbols next to each other, we get a vector where the components are given by partial derivatives. And now we have this vector in the inner product with v. And now in order to finish the right hand side here, we also have f times the divergence of v. And now you already know, divergence is just written as nabla and inner product symbol. And there you see, with this short notation, the product rule looks quite familiar because you just push the nabla operator to the first factor plus pushing it to the second one. However, please never forget that one function here is a scalar function while the other one is a vector field. Okay, and now we can do a really nice calculation by just integrating on both sides. And in fact, what we get then is what we call integration by parts in n dimensions. It's exactly the same thing as in the last video. We need to integrate over a compact volume, like a closed bowl. In that case, we have a boundary, which is a generalized closed surface. So this is the condition we have here, a compact volume that has a smooth boundary del M. Actually, we don't need to be completely smooth, because we could also deal with some edges on this surface. Indeed, the only thing we need is that Gauss's integral theorem is applicable. This is clear when we write down the integrals, because on the left hand side we have a volume integral over the divergence. And then obviously also on the right hand side we have two volume integrals. In fact, here on the right hand side you see the derivatives are either here in the first factor for f or in the second factor for v. And the only thing where both things are combined is to be found on the left hand side, where we can use our divergence theorem. This is what you know as Gauss's integral theorem from the last video, and it just tells us that this volume integral can be written as a surface integral over the boundary. This means there we have fv in the inner product with the normal vector on the surface. So there we don't have any partial derivatives anymore and just an integral over the boundary. Hence, there you should recognize the standard integration by parts formula. So maybe to see it in a better way, let's bring this volume integral to the left hand side and the boundary part to the right hand side. This means the boundary part is still positive, while the other volume integral has a minus sign in front. And moreover, if you want, we can also use the short notation with the nabla operator for the divergence. This implies that in this integration by parts formula, this nabla operator is shifted to the left hand side. Namely, there we have the gradient of f in the inner product with v. And that's it. This is the general integration by parts formula in n dimensions, which you can remember. Moreover, I can immediately show you how we can use it in a special case. We can look at the case that v, our vector field, is given by a potential. This means v is just a gradient of a scalar function g. So in short, we can just write v is equal to nabla g. And we should be precise and say that g is a C2 function. This is needed because we first form the gradient and then the divergence. And there you might already know that the combination divergence with gradient gives us the Laplacian. This is quite clear if you write down the partial derivatives. Hence you could say these two nabla operators give us the Laplacian. And just as a reminder here, Laplacian of g means you add up the second order partial derivatives. Hence the special case for our integration by parts formula is actually a formula for the Laplacian of g. More precisely, on the left hand side we have this Laplace operator, but on the right hand side we only have gradients. In fact, the only thing we have to do here is to replace v with the gradient of g. So in the volume integral both gradients are combined, but in the surface integral here you see that the outward pointing unit normal vector is combined with the gradient of g. And this is something you can recall from the multivariable calculus series, because this one is just a directional derivative. So it's just a partial derivative of g along the vector n. And one possibility for a short notation is just to use the partial d with index n. It makes sense to use a special notation for this directional derivative because it's along the normal direction on the surface. So the change of our function g into this direction is the important ingredient here. And the resulting formula we get now is what we call Green's first identity. And we already know the assumptions. We have two scalar functions f and g. The first one is a c1 function and the second one has to be a c2 function. And to make the whole formula really nice, we can bring this integral to the left-hand side. So we only have one volume integral, but with two terms inside. And now this volume integral, where the derivatives of f and g are combined, is equal to an integral over the boundary. And there, as already mentioned, the directional derivative of g along the normal vector on the surface goes in. So this is the whole formula, and definitely something we will use in applications later. However, first I want to show you that there is also a second identity, which is more symmetric. Here you see f and g play different roles, but for two c2 functions we could definitely combine them. This means we can just apply Green's first identity two times. On the one hand we have the original formula here, but on the other hand we can also exchange f with g. So instead of f we write g, and instead of g we write f. Then everything changes with the exception of this second term. Obviously in the inner product the order does not matter. And exactly this fact we can use because we can take the first formula and subtract the second one from it. And then obviously exactly the second term will vanish. And then the nice formula we get out is what we call Green's second identity. This means on the left hand side we have a volume integral of a difference, and on the right we have our surface integral. More precisely, we have two Laplacians on the left hand side and the directional derivatives on the right hand side. So you see, this is a nice symmetric formula, which is also important for applications. So what actually happens here is that the Laplacian is replaced by the directional derivatives. So you could say the second order partial derivatives are reduced to first order partial derivatives. And therefore you might already guess that this is a formula we can use for solving partial differential equations involving the Laplace operator. Hence we will talk more about that in my partial differential equations course. And there we usually weaken the assumptions a little bit because we don't need C2 functions everywhere. In fact, we only need it inside M, and on the boundary we don't need the second order partial derivatives at all. Hence, at the end of the video now, I want to formulate the theorem like we will need it later. So as before, we can describe M by an open and bounded set omega. And again, we want that the boundary is an n-1 dimensional manifold, and now we just call it del omega. And actually we just need a C1 manifold in the smoothness, which means locally the boundary looks like the graph of a C1 function. This makes sense because we just need the normal vector at every point on the boundary. And now, as already mentioned before, f and g in our integral here don't need to be C2 on the boundary, just on omega itself. But still they need to be defined on the boundary as well, so let's write it like that. But then in the moment we restrict the functions to the interior, we want to have the C2 property. But if we also include the boundary, we still want to have the C1 property because we need to calculate directional derivatives. So there you see, this is how we can weaken the property from before, and the right hand side still makes sense. However, the left hand side only makes sense if this function is still integrable over omega. So we claim that the Laplacian of f and the Laplacian of g are still integrable functions. In other words, it's allowed that the second order partial derivatives explode at the boundary, but we still need the integrability. Hence, with this additional piece of information, we still have that the left hand side is well defined. And therefore Green's second identity still works the same as before. And in fact, the proof of this extension is not so hard. because we can use our original formulation and some limit process to reach this formulation. And with that, I think it's good enough for today. You can check out my partial differential equations course to see how we use this theorem in action. So I really hope I meet you there, and I wish you a nice day. Bye bye.